Well, here's another installment of um, how to do ray diagrams and the math associated with concave mirrors. Just to review, in a previous video I showed you what happens with a concave mirror when we have the object located fairly far away from the mirror. In this case it was beyond the center of curvature, that point marked C there, and we found both from the diagram as well as from the math down below that we get a smaller inverted image, and anytime it's inverted it must also be real, and in this case it's smaller because it's located closer to the mirror between the center of curvature and the focal point. So on the other side, now on page S29, we're going to do the top figure there, number 3. I'm still going to apply the same rules for how to draw rays off of a concave mirror. These rules are summarized, remember, on page S27. Okay, I'm going to leave out the part in parentheses because those are only for the convex mirrors, the ones that kind of come out you in the towards you in the middle. And I'll draw the same 3 rays that I drew before because I think those are convenient. In the tutorial, Mr. Henderson has 2 rays drawn, but I think 3 makes it a little bit more helpful because sometimes it's just not real convenient to draw one of the other ones. So this time I'm going to do both the diagram and the math. I think I can go a little quicker on this. It's not going to take as long. So rule number 1 describes a ray that comes off of the object. Remember, there's rays going all sorts of different directions off of the object, and I'm going to come right off the top of my object. I'm choosing an arrow again for my object just because it's so convenient to draw them. I always show that the incident ray is the one approaching the mirror by putting a little arrow on that too. And then the reflection off of a concave mirror for any ray that's parallel to the principal axis goes right through the focal point. So we can draw it like that. And then a similar kind of a rule says that an incident ray that is through the focal point on the way to the mirror will reflect back parallel to the principal axis. It's not labeled on this one, but the principal axis is the little dash line here that goes right through the center of the mirror. It also goes through the focal point in the center of curvature. So it's a nice little reference line. Of course, I should say you can always pause this video as you need to do your drawings as I do mine, because I'll probably go a little quicker than you might. Now in this case, you say, well, it's got to go through the focal point on the way to the mirror, but the problem with that is to go from the arrowhead to the focal point, you're going the wrong direction. So you're not going to hit the mirror, but there's still a ray that will go towards the mirror that comes from that direction. So look how I'm putting down my ruler here. It coincides with the focal point here and the top of the object here. And so I draw a ray coming off of the arrowhead heading towards the mirror again. And that's not just some random direction. That's the one that comes in a direction that seems to come right from that focal point. Okay, and that is the ray that will reflect off parallel to the principal axis. I have little gray lines on your diagram there to help you get that lined up nicely. So that is rule number 2 here for mirrors. The rays that go through the focal point reflect parallel to the principal axis. Okay. I'm going to also do ray number 4. They hit the center of the mirror, known as the vertex. It reflects off parallel, or I'm sorry, symmetrically on the other side. So do this one in green. This one is the one that you can always draw without too much trouble. Alright, so I go, whoops, I didn't quite hit that right. This does take a little bit of exactness to really get it done well. Alright, so there's an incident ray like that. Now remember, you don't need to get a protractor to figure out what symmetrically on the other side means, because notice my object here is 2 squares away from the center of the mirror. Okay, so when I go 2 squares away and then with a height here of 4 units, that means my reflection is going to be 4 units below. You see how I'm using symmetry and congruent triangles, as they call it in math class? That's how I know the right angle. Okay, so the angle that I've measured up here, this is the incident angle, has to be equal to the angle down here. That's the reflection angle. And so now we have to imagine a whole bunch of eyeballs back in this space over here that would be seeing these reflections plus a whole bunch more that we're not drawing. and say, okay, where do those eyes see all of these rays diverging from? But the problem is there is no point that you can see yet, but that just tells you that these reflections don't really intersect anywhere. But our eyes can play tricks on us, and what the eye does is it just follows all of these light rays back and says, okay, where do they seem to be coming from? The eye doesn't really know the difference between really intersecting and just virtually intersecting. So what we do on these is, using dashed lines, we extend the reflected rays. Don't extend the incident rays. And I'm going to use the same color scheme that I used before. And so all of these reflections are being extended back with dashed lines. And we're going to see a point here. And I will tell you, my diagram is just a little bit off. But you see the spot right around there, where all of these rays seem to be coming from. I made my mirror just a little too curved. You'll notice in some of his practice that he doesn't make them quite as curved. Well, that is the location where our eyeball says the tip of the arrow is. That's what we call the image. Now, because it's on the wrong side of the mirror, remember there's no light that's really back here anywhere, we draw an image dashed, okay? And we draw it dashed to indicate that it is virtual. Right, that's an important description of this kind of mirror. I'm sorry, this kind of image. Get that out of the way. So this is virtual. And what are the other three descriptions of it? Well, you can clearly see that it's upright. And there's another rule of thumb. You might remember that every real image ended up inverted, and it's true that every virtual image ends up upright. In this case, it is larger in size. Okay, and distance-wise, it looks to be a little bit farther from the mirror. We'll get that once we do the math. So that is a description that we get based on just the ray diagram, those four things. Now I'm going to show the math using the mirror equation and the magnification equation that will give us the same results mathematically. So using the equations at the bottom of S27, I'm going to use this form here because that's already algebrated for DI. That the DI is the image distance. It tells us how far from the mirror the image is. And remember, the sign of the image distance up here at the top of 27 tells us whether it's real or virtual. So if it ends up positive, it's real. If it ends up negative, it's virtual. Then we'll use the magnification equation here to figure out how tall the image will be, and that'll tell us whether it's inverted or upright. Okay, so this looks, DI is the inverse of F minus the inverse of DO. I write it that way. Now I'm going to get my measurements here. The focal length is how far the focal point is from the mirror. 1, 2, 3, 4, 5 units. I'm going to leave the units off. They would be centimeters. So it's the inverse of 5 minus the object distance. Now this I mentioned before is only 2. Okay, so I'm going to take the inverse of 5 minus the inverse of 2. That gives me negative 0.3, and then I need to invert that. And it gives me a image distance of negative 3.3. I'm just going to stop at 2 sig figs there. I'll put my units on, box it because it's kind of a final answer. And then I'm going to see if it corresponds to what I drew. A negative image distance. That means it is virtual. And I already knew it was virtual because the light rays that are reading my eyes never really meet anywhere. They just virtually meet somewhere. And then I'm going to look to see whether it's close on the diagram. On my diagram, I have about 1, 2, 3, and a little bit more. It's actually very, very close. So about negative 3.3 centimeters. Then I'm going to do the magnification equation, which says the image height is to the object's height as the image distance is to the object distance, but negative. So the object's height was 4 units. The image distance we just found was negative 3.3. It's important to get that negative sign in there. And the object's distance was 2.0. And that gives us a height of positive 6.7 centimeters. Notice these two negative signs cancel out. Oh, I'm sorry, I'm a little off the screen. These negative signs cancel out, which is why we have a positive height. And then let's look what this means in terms of how it corresponds to our diagram. A positive image height means that the image is upright. So when you see this in the mirror, it's kind of like when you see yourself in a flat mirror, you are upright, you're not flipped over. So in this case, that's corresponding to what we drew. And a height of 6.7, if I count squares here, 1, 2, 3, 4, 5, 6, and a little bit more. I knew this one was a little bit off because I really probably, if I'd have drawn this more accurately, been a little higher here and a little bit further away. But again, as long as you're close on your diagram, it'll be consistent. All right. So there is a full description of how we do both the diagram and the math when the object is closer to the concave mirror than the focal point. All right. That's about as strange as it gets as far as images from a concave mirror. So I'm going to leave it at this, and we'll do more practice in the classroom as we need to. Play this back as much as you need to. Go back and review a drawing. Check out the tutorial, and hopefully you'll start to get this pretty well. All right, we'll see you all in the classroom.